Okay, maybe we can start. Good afternoon, everybody, and welcome to this new colloquium here at Observatory of Abruzzo. Today, the speaker will be Sebastian Hoof, and we talk about visions of action multi-messenger physics with helioscopes. Sebastian studied physics at the University of Heidelberg, including an Erasmus exchange to London, where he spent time at the UCL and the London Center for Nanotechnology. He completed his master thesis under the supervision of Georg Jägel, which is when he was first introduced to axions. He went back to UK after winning an Imperial College President's Scholarship to do this, to do his PhD at Imperial College London under the supervision of Pat Scott and Roberto Trotta. After postdoctoral positions at the University of Göttingen and briefly at the KIT in Karlsruhe, Sebastian won a Marie Curie Fellowship at the University of Padua, where he has been based since January this year. So thank you, Sebastian, for being here. And if you want, you can start the presentation. Thank you.
Great. Thank you very much for the introduction. Yes, and indeed, thanks everyone for coming. So we had this idea to have this joint hybrid seminar. So if it works well, then please thank the organizers for setting this up. And if it doesn't go so well, please blame me. But otherwise, I'm going to talk about what you can do with axions after a discovery mostly, and how this is interesting for astrophysics. Now, given the sort of mixed audience that we have here, at the one hand at the observatory, on the other hand, the members of the COST action who are very used to axions, I would just like to start with a very, very brief introduction into axions and what role they can play in astrophysics. Then I will also very briefly talk about some work that we did on the calculation of the solar axion flux and the uncertainties that are associated with that. And I'm also going to basically set the stage for the kind of post-discovery physics that you can do. And in particular, I will talk about a recent work that we did on how you can map the solar, the temperature profile of the sun using axions after discovery. And generally, if there is still time, I will also go into a few other aspects of post-discovery axion physics. So just very briefly, for those who haven't heard about the axion, so the axion kind of was first invented as a solution to a very theoretical problem, namely that basically there is a term in the QCD Lagrangian called the theta term, which is basically some parameter you need to determine from experiment coupled to or basically interacting with gluon fields. And basically, when you try to determine what the value of this parameter is, you find out that it's a very, very small number. And that is, generally speaking, something that theorists don't like. And so basically, people have come up with a way to resolve this problem by introducing a new dynamical degree of freedom, which is this axion particle. But after people studied this a bit more, it turned out that it's actually not just useful for resolving this, arguably somewhat theoretical problem, but actually these particles turn out to be, for example, as an added bonus, to be excellent dark matter candidates. And moreover, people who study sort of string theory, for example, found that once you try to compute predictions from string theory or the compactification of these spaces, you also end up with potentially a large number of these axion-like particles. And what's more is that from various astrophysical hints, like, for example, the question why the universe is relatively transparent to TeV radiation, or at least more transparent than we would maybe think it is, or also stellar cooling, which I will talk about a bit more in detail. There are also some hints where you could maybe see, or that you could use to sort of demonstrate the existence of a new particle. And moreover, so also from the theory side, I won't have time to go into this, but I just wanted to list a few additional ideas that I thought were kind of interesting to mention, like, for example, the axion mechanism, which addresses or aims to address hierarchy problem. There's also sort of a SMASH model, which unifies a lot of different solutions that have been proposed for outstanding problems in physics connected to axion models. And so overall, the sort of picture emerges that this is, not just one sort of idea that solves some niche problem in theory, but it could really be kind of a family of lots of different types of particles that either one of them or a combination of them could resolve outstanding problems in physics. Now, just to give you an idea of what we are talking about, of course, since there is such a broad range of possibilities, you cannot classify all these models in one slide, but at least when it comes down to the QCD axion, we have a vague idea of what or how to relate the fundamental quantities of these particles. For example, on the slide here, I show the QCD axion mass, which I plugged in some values for this variable Fa, which is the so-called axion decay constant, and that is the fundamental scale that you associate with the new symmetry used to introduce the axion. And the basic problem is that while it's a very beautiful solution to this strong CP problem, the not so beautiful part is that you do not know what this scale Fa is. And in fact, any scale you choose from a theory point of view would be an equally good solution for the strong CP problem. So the difficulty is that you do not know what the particle's mass is, and this is why the experimental searches are so challenging. But something you do know is that these particles will couple at some level to electromagnetism, and so the next equation relates the very specific model. So this is encoded in this anomaly ratio E over n to the phenomenological strength of this coupling. So you can, assuming you know the mass, you would be able to predict for a given model the coupling strength to photons. Of course, for these axion particles, for these string axions, you don't have these nice relations, but at least for the QCD axion, you kind of know what to expect. And then starting from this, you can think about, well, what kind of interactions do you have or can you have? And from certain considerations, like not overproducing dark matter or limits that you already have, you know that these particles will be interacting very weakly. And so basically, one thing that could happen is you produce them thermally inside a plasma, and then they will carry away energy. And so similar to neutrinos, they would influence the evolution of a stellar system. Furthermore, because you have this axion-photon coupling, they could convert in galactic or stellar magnetic fields. And also, these particles could decay. And so when you when you're looking at unexpected energy loss in, say, stellar systems, spectral lines that can associate to some transition, or more generally, for example, also spectral distortions that you don't expect, these are places where you could look for or at least constrain axion models. And I won't have time to go into this, but at the GGI school this year, there was a great lecture by Georg Raffelt. So following the link or Googling it, this will be explained in much, much more detail than what I have time to go into. But now maybe going back to the sort of cost-action audience a little bit, something I want to mention as an example for where you can look for these axions are white dwarfs. And so white dwarfs are basically one of the possible end stages of stellar evolution, with masses typically around the mass of the sun and very compact small radii. And the way that they sort of exist or that they are supported is basically not from nuclear interactions in the core or so, but basically just from the Fermi pressure that is acting against gravity. And this already also tells you that you have very high density, comparably high density of electrons. And so this is an excellent way to test axion-electron interactions. Yeah, and just for the cost of action, I mean, the white dwarf is not the big thing in the center, but the small. And so basically, what happens, or some of these white dwarfs also pulsate with a certain period associated. So basically, they have some, for example, gravity modes that will, when you look at the white dwarf, change the brightness pattern of this object. And this is sort of associated with timescales of minutes to hours. And this sort of period with which this happens changes over time, and you can relate this to the change in temperature and radius. And the change in temperature is associated with the energy loss of the system. And so what you can see here on the plot is on the horizontal axis is the interaction strength of axions with these with electrons. And if you go to the limit where axions have 0 interactions with electrons, then you can see you have some prediction for how much this period should change as you sort of as the dwarf evolves, as the white dwarf evolves. Then you can see that the blue line, the observed energy loss doesn't quite match up with this expectation. So you could fit basically an axion signal or an axion interaction strength to this observation to rectify this discrepancy. And of course, as you can maybe see from the axis already, this is a very, very difficult measurement because over the course of a year, this period is expected to change only by a microsecond or so. So you need very long observations, and there are many possible things that could go wrong with some systematics that could affect this conclusion. But at least it is something that has not just been observed once in one of these systems, but actually there are a couple of white dwarfs where there is some evidence that the expectation for the energy loss in these systems doesn't match up. So on the left-hand side, what you can see here is basically the profile likelihood for the axion-electron coupling to be in agreement with the data from these. And if you combine them in a global analysis, then you will find at least nominally very strong evidence for the existence, or fairly strong evidence for the existence of this particle. Now, as I said, this should be interpreted with a big grain of salt, more like a big rock of salt. But I think the interesting thing here is really that there is something that you don't observe just in one isolated system, but there are a couple of them where basically, this is observed. And so this is, I think, a very intriguing hint towards maybe some new energy loss mechanisms and therefore also axions. Now, white dwarfs are relatively simple in a sense that basically the axion-electron interactions are supposed to be dominant in these systems. But if you, for example, look at the sun, there are a couple more processes that you need to take into account and that could be relevant. And so on this slide, I've tried to very briefly summarize the different type of processes that we've looked at in a previous work to try and assess how many axions are basically being produced inside the sun. And of course, this has been done before, but our goal was to really revisit these calculations and look at, in particular, the associated uncertainties. And so if you look at the resulting flux you would expect from the sun in axions, then on this slide you can see, for example, if you look at the curves labeled ABC and P, so the ABC curves are the axion-electron interactions, and this curve labeled P for Primakov process is the leading axion-proton interaction. Then for different solar models, you can see, what kind of predictions you would get, and you can also see how detailed some of these solar models are. And the important thing here to take into account or to realize, I mean, it's not necessarily a very deep insight, but the spectra peak in the sort of KV scale, which obviously corresponds to the temperature of the sun. But by doing this exercise, we were able to look at the systematic differences between, for example, the different solar models. Why is this interesting? Well, there is a way that you can look for these axions coming from the sun. Obviously, you cannot see them directly, but if you point a magnet at the sun, then these axions, due to their interactions with photons, they are expected to interact with the virtual photon from the magnetic field and convert into a real photon that then can be observed. So if you put a magnet inside a sort of closed box and point it at the sun, very naively speaking, then you should see sort of light kind of inside this box, or X-rays, I should say, inside this box, even though there is no other light source. And so basically, this is the way that helioscopes look for axions. And so there's currently the new generation of helioscopes. One of them is being built in Hamburg at DESY. It's called the IAXO. And on this plot, you can see the mass of the axion compared to the interaction strength with photons on the vertical axis. And I mean, there are some other, SOCAST is an older helioscope experiment. There are also some horizontal branch star limits. But you can see that basically in this region, inside these blue curves, this is where IAXO would be expected to find axions with at least 3 sigma significance. So, and in this particular region, it wouldn't only just see axions at a certain significance, but it would actually be able to determine the mass and the coupling of these particles. And one should also stress that basically you have some expectation for where these axions should appear, and this generation of helioscopes really offers a real opportunity to discover realistic QCD axion models. So these models that are motivated by the solution of the strong CP problem. And so this is kind of an exciting prospect, but once you're thinking that you can discover the axion, you should ask yourself, well, how well do I actually know these fluxes? How good are my predictions? And so this is something that we've looked at. So here you can see the result from 10,000 Monte Carlo simulations or 10,000 standard solar models that have been generated for the high and the low metallicity class of solar models. And what we've plotted here is the Primakov fluxes. So this was labeled P in the previous plot, and the ABC fluxes, the axion-electron interactions, relative to in this case, I think it's relative to the low metallicity models. So, and one thing is to observe is the sort of mean values between these 10,000 simulated solar models is a systematic shift between these two fluxes, and this is due to what's known as the solar metallicity problem. So the fact that basically we don't really know what the sort of metallicity of the sun should be, and so there is a systematic effect which you can see here, and there's also some statistical fluctuations that are due to the uncertainties in the solar modeling, but these are significantly lower than the systematic differences. And so the take-home message is that we can do, or we have relatively precise predictions for what the flux should be. And so both are not very sizable. So we're talking about percent effect. So you can really think about doing some, using axions as a way to observe phenomena, because we know their production relatively precisely. One thing that maybe if some people are interested, I would be very happy to discuss this. I mean, there was a recent paper that claims to, well, it doesn't say it in the title, but it effectively claims to resolve the solar metallicity problem. And so there was also a recent paper that claimed to find some issues. So if some people here are interested in this, I'd be very happy to discuss. But let's take a step back to basically the computation of the axion flux, the expected axion flux. And as I was saying, we know the flux very precisely. So, okay, if you look at the flux now, I mean, on the one hand, I've shown you the spectrum. So, the axion flux is a function of energy. This is something you can see here in the 1D projection towards energy. So this is the curve you've seen before. But then obviously, if you look at the solar disk and you would think about sort of the axions coming towards you from the sun, then there's also radial dependence, of course. I mean, from the center, you would expect to see more axions than further out. And so we have been asking ourselves, well, can you use this information to learn something about the interior of the sun? Because the nice thing about these helioscopes is inside they have X-ray optics that can produce a relatively faithful that project in a faithful way the axion image of the sun onto the CCD detector. So if you were to discover an axion, you would actually see the sun in axions, and you would have the spatial information that I've showed you in this 2D plot available to you. And so basically, if you estimate how many photons you would see about the center of this image, then you could use this information to maybe learn something about the interior of the sun. Okay, so what we've done in this study that I want to sort of focus on in terms of applications, we've looked at, or we've simulated the flux that you would see in one of these detectors. I mean, this image is simplified. I mean, our detector is a bit larger. You can't have that few pixels, but just, you know, this is sort of the a sketch of our basic setup, if you will. And so basically, if you have enough pixels, then you can assume that the flux in each of these that you observe is constant. And so by integrating over these sort of virtual rings that you see as dashed lines here, you get the number of photons in each of these rings. So you basically get distribution of the photons that you observe, so axions converted to photons, as a function of radius. And then we ask ourselves, well, can you invert this? And if you look at the Primakov production rate, you will see that there is, of course, the interaction strength of axions. So there's this GI gamma factor in front. So that's, you know, just sort of factors out. And then you see that there are basically in this simplified version of the Primakov production rate. I mean, there are some more corrections for the very small electron degeneracy effects inside the sun. But to first order approximation, this is the Primakov production rate you would see from the sun. And so you can, in the formula, you can spot that there's a differential temperature. And on this Debye scale, which is the quantifies the screening scale of the sun. And, you know, while there are some partial degeneracies between these parameters, you see that some of these, so for example, in the screening scale or with the temperature, there is some energy dependence in there. And so the idea is basically, if you take this energy, if you take this energy dependence and you not only divide your signal or your data into different radial bins, but also into different spectral bins, then you can hope to break this degeneracy and learn something about these parameters. And the fundamental quantity, or the sort of physical thing that you observe, because you're looking, so or the axion flux is generated through the sun, and you're only seeing the axions coming from the solar disk. So you cannot basically reduce or break this degeneracy further. So the fundamental quantity that you can observe is what we call this gamma bar parameter. Here is some sort of integral, some spectral integral of this rate. And okay, if you then make a piecewise, if you assume that this gamma bar is given by some sort of step function, basically, then you can solve this integral, and I've done this here, but yeah, I mean, I don't really want to go into the details. Then you can compute these and the expected counts for each radial and spectral bin analytically. And sort of once you've done that, you can do a reconstruction. So basically, at the edge of the sun, you set your expected rate to 0. Then you look at the data from the outermost bin. And if you look at the formula again, you will see that the expected number of counts is proportional to the value of the step function at this point. And in the next to outermost bin, you will see that there are some factors involved that depend on the bin size and so on. But effectively, it's sort of a sum that you are generating. And so basically, as you come to the middle, there is some factors involved, but basically the rate for this interpolation is given by the sum of the counts, the expected counts. And if you then set equal, I mean, you can also write this as a matrix, but the point is, if you then set the expected counts equal to the counts that you have observed, you can analytically invert this and also propagate the uncertainties and fit the corresponding parameters. Now, this is a very nice, analytical scheme and a nice exercise, but it will be some sort of step function which is clearly not physical. And so what we tried is some different ways to approximate this. We used some splines, and also there is also some other nasty feature of this, which is that you can only do this inversion, this analytical inversion, if you have 0 counts in more than at least 1 count observed in each of these bins. And so this is very restrictive. And in the end, we decided to just make shape-preserving spline interpolation, so a spline that cannot sort of ring and go into unphysical values. But this is basically not you cannot nicely illustrate this, and so, because it's just a forward-fitting procedure. But the sort of logic is very similar to the this analytical inversion that I've shown you before. So the basic idea is to have these parameters, these spline parameters at different points inside the sun, and then basically compare to the or infer these parameters from your data sets. And what you will find is a reconstruction of the temperature and the Debye scale. Now for the temperature, as you can see from this plot, you can actually reconstruct the temperature profile of the sun pretty far out for these given values of the coupling. And I should maybe say that so the sort of optimistic case is just below the current limit. So this is the most optimistic case for when IAXO gets switched on. And we will observe the axion within a few years with over 330,000 photons or 330,000 axions. And then you can do a very good reconstruction of the temperature all the way up to 80% of the solar radius. In the less optimistic case, where you only have 250 photons to work with, I think it's still a pretty decent reconstruction of the temperature. But in either case, because the mathematical dependence of the Debye scale and the degeneracy is a bit stronger, and actually this approximation that we used for the rate plays a bigger role, you cannot really get a similarly good result for the Debye scale. So really, this method gives you a pretty good reconstruction of the temperature profile, but not so much of the Debye scale, which sort of encodes the some weighted sum of the element abundances in particular. Now, of course, you can say, well, axions, we don't know if they exist, so could you do something similar with neutrinos? And we've thought about this, but so if you look at the sort of scales of this plot, this neutrino image that the Super K collaboration has produced, you cannot really do this because the angular resolution is just not good enough. So you don't have the same spatial resolution as for the axions. And so really the X-ray optics that you can make use of in helioscopes help you with that. And one other thing, so again, this is a plot of the axion mass and some version of the photon coupling. I mean, this is just, again, to try and visualize what is happening in a fitting procedure. But you can, once you observe something, you can think about running your analysis chain once with one of the high and one of the low metallicity models. And so this plot is just a way of visualizing the discriminating power between these two models. So if you look at for example, sub-panel A, this would be a case of a very high signal. And here the analysis, the forward fitting, I mean, the chi-squared would at the end tell you that if this particular benchmark point or this particular axion model exists, that you could, or if this is what you find, then you could discriminate, or you could at least provide a hint towards resolving the solar metallicity problem. And also, because you can see in the bigger panel that there are discrete lines. These correspond to 15 different selected models that you could even, you could even say, okay, I will, this is a model, this is my actual UV implementation of the QCD axions. You will have not just a detection, but you could, assuming that it's a QCD axion, one of these 15, you have a hint towards identifying the UV structure of these models. Now, these are 15 selected models, so a bit later on, what I've also done, and other people have also done, is to create catalogs of all of these models, and then, this wouldn't be necessarily possible anymore, but at least with these catalogs, if you get really lucky, you can still do the same exercise with IAXO. Another thing that you could do, and this is something where really axions can in some sense shine, is to look at the macroscopic magnetic fields inside the sun. Now, as you can see from the plot, so on the plot you see the magnetic field strength, or this hypothetical model of the macroscopic magnetic fields as a function of radius and the strength. And you can see that these like the boron neutrinos and so on, I mean, these put limits on how strong the magnetic fields can be. But crucially, there is no measurement of these macroscopic magnetic fields which should exist. And so far, it has not been possible to provide evidence for, at least to my understanding, evidence for the existence or to measure these. And so with axions, you know, these works cited here really show that you could measure these fields with axions. So again, looking inside the sun. And then perhaps something a bit also related to astrophysics, but not stellar physics anymore. There's a different type of experiments called helioscopes, which are basically cavity experiments where you tune the resonant frequency of the cavity, you know, as you sort of, so you basically tune to some frequency and you just wait for a sufficiently long time, and then you tune to the next frequency. So basically like tuning a radio. And the idea is that eventually, if you hit the a frequency that corresponds to the axion mass, you would see an enhancement in the signal, or you would see a signal due to the matching of the resonance, due to the matching. And the power spectrum that you can observe over time will encode information about the speed distribution of axions as dark matter particles as you continue to observe it. And so what these other authors have shown in this plot is you would be able to determine the speed dispersion and the relative speed of the halo over the course of a measurement. You can see that after a year of sitting on your axion resonance with these experiments, you would be able to get a very relatively precise estimate for these quantities, which are notoriously somewhat difficult to measure. And if you look at the frequency space, another thing that you can do is, again, sitting on this resonance for the axion, if it exists, after a decade or so, you can also see you can see tidal streams popping up in the data. So you would be able to really see the sort of substructures of the halo as we move in our local dark matter. All right. So to summarize, I hope that I could give you an impression of why the next generation of axion helioscopes are exciting, and not just from the perspective of a particle physicist, because of course there are these theoretical problems at the core, or at least these problems are those that a lot of us find fascinating. But from a phenomenological perspective, axions are very similar to neutrinos in some sense, that they can influence the stellar evolution. They can potentially explain some of the astrophysical anomalies that we've seen. And so, thinking about or hoping for an axion discovery, one could envision a stage where we can use axions as messengers from the interior of, for example, stars, to study the properties of our local dark matter halo, if they are an important component of the dark matter in the universe. And the particular example that we've looked into is the reconstruction of the temperature profile of the sun. But you could think of many related applications, some of which I've flashed in the end. And to sort of support these efforts, myself, but also other people, are developing this a number of open source tools, which I've also linked here on the slide. And this is I think something that is very nice, because it basically enables you to use these results, these theoretical computations, to do some at least what I think is exciting phenomenology. And so with that, I would like to thank you and open the floor for questions.
Okay, thank you, Sebastian, for this nice presentation.